Hello and welcome back. In this lesson, we will study addressing modes in assembly. Let's start first by discussing how assembly instructions work with operands. An operand address tells the computer where the data to be processed is stored. Some instructions require operands, while others don't. Depending on the instruction, you might need 1, 2, or even 3 operands. The first addressing mode we will cover is called register addressing. In this mode, data is stored in registers. Registers act as temporary storage locations within the computer's processor. And as I mentioned before, and depending on the instruction, registers can be used as the first operand, second operand, or both. For example, the instruction move dx, tax underscore rate. This actually assigns the value of the tax rate to the dx register. Here, the register dx acts as the destination operand. So in the first line, the register here is the first operand, dx. In the second line is the second operand, which is cx. And in the third line, actually, both operands are registers. The next addressing mode is immediate addressing. In immediate addressing, one operand is constant value or an expression, and the other operand can be a register or memory location. The constant value is directly provided as part of the instruction. For instance, consider the instruction add byte value 65, which is on the third line. Here, the immediate operand 65 is added to the byte underscore value. The first operand, byte value, determines the size of the data. And in the first two lines, those are variable declarations. db stands for define byte and dw stands for define word. And once those variables are ready, we can add the immediate operand to those variables, in our case, byte underscore value. And if you will take a look to the fourth line, you will find that there is an immediate constant 45h, which is transferred to the AX register. Very important note about immediate addressing before we leave it, that it's very useful when you want to perform operations with fixed values that don't change during program execution. The next mode is memory addressing. In direct memory addressing, one operand refers to a memory location, while the other operand references a register. A very important note about the memory addressing here, that it's slightly slow since it involves accessing memory. For example, the instruction add byte value DL. This here adds the value stored in the DL register to the memory location byte underscore value. However, in the second instruction, the operand from the memory is being added to the register BX. Another addressing mode is direct offset addressing. This mode modifies an address using arithmetic operators, and it's commonly used when working with tables of data. So let's say we have a table called byte table defined as db 14, 15, 22, and 45. To access the elements of this table, we can use instructions like move cl byte table and 2 in square brackets, or move cl byte table plus 2. Both are correct. These instructions actually retrieve the third element of the byte table. The last addressing mode we will cover is indirect memory addressing. This mode leverages the computer's ability to address memory using segment. In fact, base registers like EBX, EBP, or BXBP, and index registers like DI and SI are used within square brackets for memory references. Indirect addressing is particularly useful for variables that contain multiple elements, such as arrays. The starting address of an array is stored in a base register like EBX. To access different elements of the array, we can use instructions like move EBX myTable to load the effective address of myTable into EBX. Then we can perform operations like move EBX 110. And this is to assign a value to the first element of the array. And then we can perform operations like move EBX 110 in order to assign a value to the first element of the array. And speaking of the move instruction, throughout the last videos we have mentioned the move instruction several times. So what is move? Simply, move is used to move data between storage spaces in assembly language. And the syntax of the move instruction is straightforward. Move, destination, source. So we are moving the source, which is the second operand, to the destination, which is the first operand, as we saw. Not to mention, of course, that the destination and source can be registers, immediate values, or memory locations. So let's go ahead and write a small program to illustrate what we have discussed in this lesson. Alright, so let me go ahead, go to my home directory. I'm going to, let's just check out what we have. Okay, so let me create address modes. And here I want to create a file. That's the main file where we're going to be coding. I'm going to use NeoVim. You can use Vim, Nano, Emacs, Visual Studio Code if you want. But for me personally, I prefer NeoVim, and that's the code editor that I'm going to work with today. Test.asm. So this simple program that we're going to write basically writes original names, so name and surname, to the standard output, and then changes the name to a new name, both actually, the name and the surname, and writes the new name and surname to the standard output next to the old one, and finally exits the program. So that's basically what we're going to be writing. So the first thing that I need to write naturally is the data section. And the data section, as we know, is used to declare static data that will be stored in memory. So I'm going to declare a variable called name, and I'm going to be using the db directive. That stands for define byte. And we want a string, and I'm going to enter John Doe. So the John Doe name is going to be stored in the memory with a length of 16 bytes. And that's going to include that null numerator here. So we can say here original name. Okay, so that's the first section. In the next part, I need the text section. So section.text. And naturally, I need the entry point of the program, which is going to be defined here, global_start. And that global directive is used to indicate that _start is accessible from outside the file. So start right here, column. Now we're going to write our program, our first code block. And what we want to do is to write the original name to the screen. So let me add a comment here. We'll say writing the original name. First of all, I want to set the value of the data register, the EDX, to 16. Okay, and that represents the length of the message to write. Next, I want to load the address of the name variable into the count or the counter register. So move ECX name. Next, what I want to do is to set the value of the EBX register to 1. And that represents the file descriptor for standard output. I think you know that by now. Also, I want to move 4 to the accumulator register. And that represents the system call number for sys_write to write on the screen. And finally, we want to trigger a software interrupt syscall. You can do syscall, by the way. That's mostly used in the X86 64 systems. Okay, but for us here, we're going to use, as we're working with the 32-bit systems, so int 0 by 80, and that naturally just transfer the controls to the kernel that performs the specified system call. In our case, of course, writing to the standard output. Okay, so that's calling the kernel. This is system_write. That's here loading the name address to ECX register. And here simply is the length of the message to write. Now we want to change the name to the new name. Here we are going to move 32-bit, which is 4-byte value that represents a string with the new name. So the new name, so I'm going to use the word, which stands for double word. There is also quad word, or the Q word, which stands for quad word. But in this case, we are going to just move that 32-bit value, or 4 bytes, because each byte equals to 8 bits. So 4 multiplied by 8, that's 32-bit. So the name here, and by the way, each byte represents one character. Okay, so we will have 4 bytes. That's the name Jane. Okay, I'm going to write that in the comment, don't worry. So move double word in square brackets. We will enter the name, and the name here is Jane. Okay, so that's moving the 32-bit or 4-byte value to the name. Okay, so right, so I hope this is not a mystery to you. I don't know, should I write this or not? So each 1 byte, I think you know this, guys. So each 1 byte equal to 8 bits, and each 8 bits represent 1 character. Each 8 bits, basically, it's the zeros and ones. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. For example, that might represent, I don't know, any character, A, B, C, D, and so on. So as we have here 4 characters, each character of those is represented by 1 byte or 8 bits. That's why we are moving those 32 bits value into the memory location pointed to by name, right? I hope this is clear for you guys. Next, I want to do the same thing for the surname. So we'll do that in an awkward way, but I hope it will make sense. Name plus 4 now. And that's going to be, I want Jane Smith. Yeah, so 4. So that's actually, okay, that's actually 4 also. So that's 32-bit as well. So again, moving 32-bit, etc. And we need also the H. So name plus 8. That's the location. That's the memory location that's going to start from. What's going to do the assembling. So we need the H as well, and let's have space after, or really doesn't matter. Okay, that's also moving the 32-bit, not but, bit, 32-bit. And now I want to move 1 single byte with the value 0. Okay, that's 8 bits. So move byte, name here plus 15. Again, that's the memory address location. 0, and that's called null terminator. Moves that into the memory location name plus 15 to null terminate the new name, by the way. So it just blocks it. It's a punctuation after the name. So again, we are going to write the same code. That's the same thing we're going to do for the new one. So let's do that very quickly. Writing, that's the length. That's the message to write. That's the file descriptor, the standard out. That's the system call number for system write. And finally, calling the kernel or interrupting the system. Next, I want to exit the program. So I'm going to system call 1 to sys_exit, move EAX1. That one is a bit new for you guys. XOR, which stands for exclusive OR. That's a logical operation that compares two binary digits or values. Basically, it returns 1 if the two inputs are different, or 0 if the inputs are the same. Why do I need it here? Well, I need that XOR operation on the EBX register with itself, effectively setting the memory or the register, the EBX register, to 0, which represents the exit code 0 here. XOR EBX, EBX. And that's also very common in the 64-bit architecture. And again, we are going to call the kernel 0 by 80. That's exclusive OR, returns 1 if two inputs are different, and 0 if two inputs are the same. All right, and that's basically it. This is our program. Save that. Now let's go ahead and assemble our program. NASM FELF64 output test.output from test.asm. I have a typo. Apologize for that, guys. Where's that typo? Oops. Okay. Let's run that again. Okay, perfect. Now we need the linker. If you don't know what is the linker, you can do man ld. That's the GNU linker, basically. Okay, combining a number of objects and archive files, relocates their data and ties up symbol references. If you don't know what is LD, you can check out my first video. I've explained what is LD and what is a linker and what it does basically in order to assemble our program. Okay, but for now, let's quit and let's do LD test.o. We want an output executable, and let's also call it test. Okay. Now we have that executable file on the left side, test. So to run it, and there we go, John Doe, Jane Smith. That's basically the old name and surname and the new name and surname. All right, so that pretty much wraps it up. Thank you so much for watching. In the next lesson, we are going to check out the variables and constants in assembly.